Correct. Good. So without further ado, let's go ahead. This is going to be the second session related to the production system analysis. As you're aware, 2 weeks ago, we had the first introduction session on PSA. We call it PSA, in which we created a library that you can all use. And in fact, the idea of today's presentation is just to refresh, do a very quick and dirty refresh on the previous one, just to get some basic topics, fresh in your mind right now. We also made a very small updates on the library, especially we just clean it up and remove some printings that they were appearing in the past. So now I think it's better. And then hands-on on an exercise is going to be I think it's going to be a very more applicable exercise, and you all are going to enjoy. So you feel free to participate at any time. So you can write a question if you will, or if you want to wait until the end, it's up to you. It's very open session. We have no fixed format, so feel free to participate and make this session more interactive. Okay, this is what we were talking about last week during the previous sessions. So today what we are going to be doing is what we call nodal analysis. And the nodal analysis in today's session is going to be concentrated on the SAM phase. So we're going to see where the vertical performance of my configurations and the reservoir deliverability, they intersect in the operating point to obtain what we know the operating rates. So, but just to refresh, we have a very simple Darcy model, which is it can be obtained just by having production data and production pressure data, or we can also estimate it using reservoir properties like permeability, thickness, and radius. We know very well that the Darcy equation is applicable only when we are in a monophasic situation, which is when my reservoir pressure is above the saturation pressure, in order to have this linear relationship. So my IPR is basically the inverse of my productivity index. Every time my reservoir pressure is above, or my flowing pressure is above the saturation pressure. And we know what happens when it's going below. We have many models for today's sessions, and also on the PSA, what we are using is Vogel equation. And as you know, Vogel requires, as it was stated, it's just a study with the different depletions and different type of IPRs. And it came out with kind of a unique or a normalized IPR. And the expression is that one. And you can see that the only data that we need to have in order to define the IPR using Vogel is a well-test data. Of course, we need more than 1 point of pressures and pair of pressures and flowing pressures and rates to estimate rates, and also the maximum deliverability, which is also known the AOF, absolute maximum performance. Okay. But as you can see in this equation, we don't see any reservoir properties related, or we don't see relation with the skin. We don't see relationship with the permeabilities. So what we're going to be assuming is that, and this is a normal assumption, at reservoir pressure, whatever reservoir pressure I have, if my reservoir pressure is below the saturation pressure, everything that is above is linear. So imagine that we can extrapolate beyond my saturation pressure. So in other words, we have just right behind the reservoir pressure linear relationship, and right below is going to be a saturated reservoir. So if we equalize both, there is a way we can manipulate. We have a Darcy from one side, Vogel from the other side, and we can have both integrated. And it's just very nice ways now that I can integrate Vogel's with Darcy data. Okay. And this is essentially what we were just saying, but just extending in a reality when we have my reservoir pressure, my static pressure. It might be above the saturation pressure, my bubble point pressure. But sometimes in my deliverability curve, my pressure falls below the saturation. So we may have two types of IPRs. So one is going to be a linear IPR, and for the rest, we're going to have a non-linear IPR, on which we can use any models. We have Fekowicz, we have CNN, we have Darcy. There are many, many models, Darcy, no, sorry. Many models to define a IPR for saturated reservoirs. But in essence, what all the models or all even the software they do, they have these combinations. Everything that is above the saturation pressure is going to be linear, and you're going to be using Darcy or any other way to have a productivity index. And the everything below, you use the model that you selected. For our case, we're going to be selecting, as I said, Vogel. So keep in mind something that is very important, that when we define here the slope, or the inverse of the slope is the productivity index, or the inverse of the productivity index is the slope. So this is valid, as we say, only, I mean, at any time, at any point of the curve, because it's linear. But what happens when we are in these situations? So if I do my calculations of J, or productivity index, it's going to be, I mean, same slope, this part, no problem, but what happens here? So we have a productivity index changes anytime on the curve. So the assumption is we have two ways of doing this. We have a characteristic IPR, which is nothing else, or characteristic PI, which is nothing else than the productivity index at the saturation pressure, just right at this point. So it's telling you the slope of the curve at the saturation pressure or the static pressure, depending where we are. But if we want to be unique, what we really should be talking about is about this point, which is the maximum flow, which is unique. No? So any curve, no matter if you are linear or if you are, I mean, combination of those, I mean, you have a unique AOF or a unique maximum absolute open flow, okay? So if you see in modern literature, they refer mostly to the AOF instead of referring to the PI. But keep in mind that we are dealing with, you need to know what we are dealing with. No? So in our case, when we say, okay, my PI, and if I know we are below the saturation pressure, we are talking about is the slope just right at the saturation pressure, okay? This is just clarifications for the PI. So we also have in the library, for the PSA library, we have something on the multi-phase flow, very basic, well, it's not a basic, but it was one of the good approaches developed in the 70s. We have Bex and Brill, and we also have Hagedorn and Brown. But in essence, we have a way to calculate this curve, which is the pressure gradient, given the Weber configuration, and also the type of fluid that we are going to be dealing with. So without further ado, so let's hands-on this. Just to refresh you, the libraries that we are going to be using in Python, you're going to be dealing with NumPy, the psapy, and which is where we develop all these equations, the SciPy, Matplotlib, and Seaborn as well. Okay, let me change now. So if you have any doubt, let me know. Otherwise, I will continue. Let me now check this. All right. Can you all see now? Well, the Chrome and the Jupyter Notebook. It's good, the font size. Let me try to increase a little bit more. Okay. So, okay, before this, let me refresh on the previous one. I'm sorry about that. Okay. This is what we were dealing last week or 2 weeks ago. Okay. Just to refresh you, we use Bex and Brill, and there's different ways to, we started with the pressure gradient, okay? And for the pressure gradient, it's just a way to calculate flowing bottom-hole pressure at a different depth, okay? Using Bex and Brill, the Bex and Brill correlation. And remember that for the input data, we need to calculate this pressure. And when we're talking about this pressure, it's tubing head pressure, tubing head temperature, oil rate, water rate, GOR, gas gravity, oil gravity, water gravity, D, which is the diameter of my pipe, and also the angle. We said last week that for sake of simplicity, it's going to be a vertical well, so it's going to be 90 degrees all the way down. But if we have, in case we have a deviated well, is where we have to incorporate the deviation survey and split this problem into different phases or different parts. And every single piece or segment or part, you have to do the calculation for every segment and then integrate, okay? So the beauty of that, if you're coming from the old school, you remember we have the Brown curve, and when you have a lot of type curve and you use some type curve and you input with the tubing head pressures and given the depth, you calculated the bottom hole pressure for a given well configuration. Now we have a way to compute that, and it's going to be it's very powerful, and there are many correlations for doing that. But in this, what we having is a way to compute, as I said, my flowing pressure as a function of depth for a given flowing conditions, rates, and for a given configurations, like a pipe diameter, angle, deviation. And we did some exercises just by changing, see how the oil rate affects the pressure traverse in different conditions. And especially what we're dealing here is we are having different way or different, how the friction is affecting my flowing pressure, okay? This is from the VLP standpoint, or from pressure traverse. Then if we want to go further and do the VLP, the vertical lift is going to be the solution point at my depth. And in this case, the depth is normally referring to the sand phase. No? So if we use the same equation, but instead of having the pressure traverse, we just get the last point of the pressure traverse, and for a different rates. So we have a way to estimate the what we call the vertical lift performance, which is nothing else that flowing pressure at the sand face at different rates conditions, okay? So we basically are changing the rates, maintaining all the other parameters constant. And also we have, what we did last time is a way to estimate the rates for a given pressure. So we use the solver on Python to estimate what the pressure, what a possible solution on oil rate would be for a given tubing head pressure. But we also observe that, I mean, if we have here, let's assume we have a fixed pressure of 1800, we may have two different solutions. So because of the nature of this curve, we have multiple solutions. And we know one is, we have a negative slope and then positive slope. So we have one region where the well normally behaves unstable, and the other solutions is referring when the well behaves stable. Okay, for the IPR was very simple. On the IPR, we just input this very simple function where we just input reservoir properties and the number of points of my IPR, and then I'm going to be displaying my IPR. We do the same for linear, VOGEL'S, and also the VOGEL with IPR. And it was very straightforward. So not rocket science. So two ways of showing how the library seems to be working okay. So now what we're going to be doing today is working with both the IPR and the VLP just to obtain the intersection point, what we call the operating conditions. And it's going to be, I would guess, more interesting. So let me change my display now. All right. So we're going to be publishing this also on the site. So, but before starting, so keep in mind that if you already installed the psapy library, I would recommend you to update. So pip install psapy minus update, I guess, or upgrade. That should be upgrade. There you go. So, of course, I already updated mine, but if you haven't installed, you can install it. If you have it already installed, just make sure that you upgrade it. And we can clean some dirty stuff right there. So let's move. Let's begin with the action. Now it's going to be very interesting. Okay. Very similar. So we're going to be importing the libraries. NumPy, Panda, Math. I don't think we're going to be using Math, to be honest, right here. Matplotlib for plotting. And we have within the psapy, remember we have fluid probes, which is the library related to PVT correlations. Into the psapy, we also have Bexambril. I'm just alias Bexambril as a BB right here, just for short and simplicity. For the IPR, in the IPR, we have the library VOGEL. So within VOGEL, I'm using this called APR. And we are going to be using also SciPy. Last week we used the optimizer and interpolation. Okay, the input data is very similar to same type of information we did last time. And it says, it's not a real data, it's just data I just invented. Let me refresh you that we created this very simple function for the temperature gradient. It's just a way to input temperature gradient for every, for different depths. After the temperature gradient, we can calculate, we have a vector of depth, okay? In this case, we're going from surface to the depth, which is defined right here as 5,000 feet. Everything here is on oil field, and the sample size is 51. So we are talking, we are dealing with 51 values of depth. For each one of the depths, we're going to be calculating the temperature. Okay. Another value that we know we need for sure is the saturation pressure. So for that, we use the fluid probe library, and in this case, the PBOP is the function to calculate saturation pressure using standing equation. And that condition leads me to a saturation pressure of 1488. Simple. And last time we were using this function to estimate the pressure traverse for a different oil rates. In this case, we just expanded a little bit. So if I can also play with the diameter, or we can play with DOR. In reality, we should be expanding the input of this function to all the variables that affects my VLP. But for sake of simplicity, we just maintain this very simple. Something that is not here, but let me put it, is the other function to calculate the VLP, which is using the previous function of pressure traverse. And which just basically is extracting the last value of my pressure traverse, as I mentioned, and appending every value into a vector. The output of this is going to be a list of bottom-hole pressures, okay? So we're gonna have a pair of rates with pairs of PHP. So let me just test it. Okay, I haven't. There you go. So we have a list of flowing pressure calculated for this pair of rates. So if we plot these, we should have the VLP, okay? And you remember last time we calculated the IPR as well. For the IPR, we use the Vogel equation with the Darcy. So if my pressure In this case, the input pressure is 4,000 psi, so that's my reservoir pressure. And I know the saturation pressure is 1488, so we are gonna be in the situation of the combined IPR. So which is my default case. I mean, no matter if you are above or below, the Vogel-Darcy function already considers and check the conditions, and based on the conditions, it will decide what to use. So we have my IPR, and then we can plot it. So let's do a plot of the, say, VLT plot. And remember, the output of the IPR is two pair of pressure and rates. So the first is the rate, and the second column is the pressure. So if we do semicolon, so I just avoid it. That's fine. So we have the IPR. Let me do some Dolce Gabbana here. So just to make this nicer, put this bigger right here for all of us. Make some labels. Nice. All right, nothing else, no rocket science. It's very simple. Now let's incorporate into this plot the solution of the VLP, which is these two guys. So I'm going to add the other solutions. So we have rates, and we have BHPs. And then I'm going to say that the marker side, the marker is going to be dash. There you go. We need to. There we go. So we have the classic VLP IPR, and this is the classic nodal analysis exercise. When we have some condition, let's see if we have operations. Or when I say operation, we have intersection between the two curves. And just from a graphical perspective, we know we have it. Okay, and we know that my solution should be a number between 2,000 and 2,500, probably 23 something. So now the next phase is, let's work a little bit on the intersection. So let's use some libraries to estimate what the solution point is. And it's going to be interesting. So for this, we are going to use one function from the psapy, which is the least square. And we are going to create an objective function. And also for that objective function, there's nothing else. We are going to be comparing, okay, for every point on this curve, pressure right here, pressure right here. And what we want to do is minimize this pressure, or this delta pressure. So the problem is going to be a minimization problem when we have the difference between this curve being zero. Also keep in mind that we may have two possible solutions depending on the characteristic of my well and characteristic of my reservoir. So for this case, and for sake of simplicity, we are going to be using the single point intersection, but keep in mind that we might be dealing with two. So the other thing that we need to consider and be aware of is, let me see if I can make some. markers here. Yeah. So the reason I'm putting the markers right there is just to show you that we have points. So it's not a continuous curve. And last week, or last session, we spent a couple of minutes just saying that this is not a continuous function, it's just a vector of points that we need to somehow make it continuous. And a way to make it reach continuous, there is an easy way, which is interpolation. So you can do a regression, and this is some softwares they use a lot for the IPR regressions on the form of the C and N. So it's the delta pressure and a coefficients, and they do a regression, and that may work. And you have an equation that is defining this. I mean, if you feel comfortable with your curve, and if your points are defining very well your IPR, I don't think there is a need to complicate or to overcomplicate the things. No? So we can do interpolation. So for the interpolation, if we recall, there is a function called inter1 PD, inter P1D, sorry, from SciPy. And I recommend you to go into the library and check all the inputs for this, because there are many advantages of using this. You can do interpolation between, 2D or 1D interpolation between two curves. But if you have many vectors, it can also do interpolations using vectors and using matrix and something more elaborated. So it's very powerful. So if we use, let's go and define a function for the interpolation of the IPR equals to the okay. And for this, the input, I need to know for my IPR the pair of pressures and rates. So for pressures, we have, let's make it for simplicity right here. Let me put, for sake of simplicity, let me define IPR rates. Is that one? IPR pressure, is that one? So I'm going to be passing to you, this is my X values. So this is my Y values. Okay. And there is another, we have many arguments there, but one of the arguments is the type of interpolation that you want to. So remember, interpolation normally takes place between the two nearest points. So in this case, linear may work, but if you want to make sure that it's working anytime, I would suggest to go into the cubic. So cubic. And we can do the same for the VLP. So what we have here is just two functions to obtain the VLP and the IPR for any value of rate that we assume, okay? It's very simple. And of course, we are taking advantage of this powerful library. Then, as I mentioned, we have to define an operating function, which is nothing else than the difference between the two pressures, okay? And that's what the optimizer needs to minimize. So in this case, let me explain this objective function. The only argument we are passing right now is an initial rate guess, okay? And it's going to estimate what the bottom hole pressure is for the guess, for the IPR, and for the VLP, and it's going to return the difference between these two. So in other words, we are going to, it's going to evaluate for a given rate what the pressure is for the IPR and what the pressure is for the VLP. And the next one, say solution rate is going to be equals, now it's when we are going to be using the least square function. Okay. And if you check the help, you're going to have a lot of informations and in terms of the input and output. But what is asking you, I mean, no matter what, is an objective function that the default is needs to be minimized. So it's going to do a lot of some iterations following some algorithm in order to minimize minimize the difference between these two curves. So I'm passing this the objective function that I'm using. So keep in mind this is the same name right here. And also passing an initial argument, okay? And this is important, be careful on what you're passing to. If my initial value is too high, for example, I'm passing 3,500, so it's going to fail because it says, okay, this is above the maximum value of this, okay? I normally pass a value, you need to make sure that the value we are passing cover both the IPR and the VLP. And I normally pass in the maximum rate of the IPR. That for my solution, just graphically inspected, I see, okay, it covers both, okay? And there is also an argument, it's optional, which is the bounds, no? And this is for the optimizer. So I'm going to be searching for my solution in this domain, I would say between 0 to maximum rate. So I don't want, in other words, I don't want you to start extrapolating here. Okay, so if everything works fine, and I hope so, no. Okay, VLP rate is not defined, okay. VLP rate is in reality is BHPs. Which is the two. So in the previous exercise, I rename it. Maxwell, okay. Let's do this. Let me call Maxwell equals to the maximum value of the APR, which is supposed to be the AOF, and we can be consistent. There we go. Excellent. So we see that now the solution of the optimizer say, okay, we have many outputs, cost function, the gradient, the Jacobian, a message that to let you know the condition is satisfied. So we found a solution in 8 iterations and success equals true. And this famous point is the solution. So it's 2346, which seems to be fine. Pretty much very close to what it said. So another elegant way, so I can extract from this array the values of X, right? And you see the solution because it's within an array. So I want the 0 position. So we can also extract 0 position for the first position. There we go. So my solution rate is 2346, which is pretty much in line to what we observe here graphically. Nice, huh?
So Nacho, you probably wanna you probably, it will be very interesting if you can plot a vertical line, redo that plot with a vertical line located at the solution, so we can see that it actually intersects more clearly.
Oh, yeah. So for that, I just need to, if I can, yes. I guess it's going to be for the X. X value is going to be in a solution rate. And the dx value is going to be 0, 4000. There you go. Like this?
Yeah, that looks great. So there is another way to do the vertical line. Matplotlib has the option to draw a vertical line, but that would be something that can be investigated next. So it's I mean, this fulfills the purpose. This is what I was suggesting. But there's also an option in Matplotlib to draw a vertical line or horizontal line, so you can you know, express something with the plot.
Yeah.
But this one works good. Yeah.
Thank you, Adolfo.
Yeah.
So I just want also to show you that we could do also the same, but without, instead of doing the interpolation for the VLP, we can use the VLP online. No? So the only change we have to use is, instead of using the interpolation function, we are going to be calling the pressure traverse function and obtain it. So let me show you this. It's not a big difference. This is something that I want you to stress right here. It is something like this. Okay. So there's the same, practically the same operating functions. The IPR from the pressure from the IPR is going to be interpolated, but the pressures from the VLP are going to be calculated for every single point. So if we say max, we do this, yeah. You see, we all have the same solution, of course, and it seems to be the same, but it does have some price, and the price is the computational price. So in this case, I have, I would say, a pretty decent computer in terms of resources. But if we use this decorator, we call time IT, so it is the iteration time for this, and let's compare this iteration time with this one right here, just to give you an idea. So currently it's working, so it's taking more time just because it's calculating the iteration time. But it said, okay, I have my solution in 5.9 milliseconds, okay? Plus minus 106, whatever unit is this. We do the same for the calculations online. So we have 385. So it's pretty significant. I mean, the difference in terms of computational effort that we have to obtain this. So that's another way I want you to reinforce my message of using interpolations or any other quick and dirty method. So it's not going to cost you too much in terms of the solution. In fact, we are getting exactly the same solution. But the price or the benefits in terms of optimizing your resources is very huge. For a single point or for a single well, that's not a big deal. But if we are dealing with thousands of solutions, so you're going to be paying the price very quick. Also, if we are going to be developing any type of optimization algorithms or neural network or machine learning, if you go to this route, it's gonna take for sure probably 10 times more than the other one. Okay. Good. So now let's make this a little bit more interesting. So we know we have my IPR, my VLP, and there is an easy way to have my intersection point, and this to be fine. Of course, I started on this and I constrained this to use the maximum value. But if we started with the minimum, most likely the solution that the system is going to find is going to be the unstable part. So if you will, you can have a way also to have the two solutions if exist. Okay. So now let's deal in a more exciting, going to sensitivities. This. Okay. Now I want to have the same type of solution, but instead of having a single reservoir pressure, I want to make a sensitivity on multiple reservoir pressures, okay? The procedure or the workflow is basically the same, but the only difference we have is that in my objective function, I need to pass something else than just the rates, okay? And in order to do that, let's define or redefine my objective function, okay? It's very similar to the other one. Rates. I guess. Yeah. It's very similar to the other one, but in this case, we are passing multiple arguments. So we're passing the initial or the guess rate, and within a tuple, we are passing also data, which is additional arguments, and we know that the first argument has to be the rates, the second is the pressures, the VLP rates and VLP pressures. So I'm just passing the vectors. Oops, sorry, he's saying. I'm incorporating the vectors to do the interpolation within the function. It's nothing else like that. Okay. In this function, we were having a fixed interpolation. In this one, now we are just incorporating the vector as a part of the arguments. So let me see. You will see more clearly right here. So if we redefine here the rates and pressure is exactly the same. Let me do this. Instead of pressure now, I have a vector or a list with, in this case, 4 values. Okay. Let's do an iteration. Let's go through every single value of pressures. We can have a discussion whether or not this is the best approach. I'm trying to be probably more academic, but there are ways or better ways to do this without going into iterations. But also you may lose the track on especially when we're having different variables to optimize or to sensitivity. So let me go into the details. So we are going into the pressures. For each one of the pressures, I'm going to calculate my IPR. That's fine. This IPR I'm passing now into the data tuple. So this is the IPR, the solution from this, the solution from this. And the maximum value is going to be the maximum IPR value, and solving the same equation. And now I'm saving the solution rate for each one of them. Okay? And at the end, we do a line plot with the IPR and the VLP. So solution rates is not defined. Perfect. Yeah, we need to have an empty array. Here. Solution P is not defined. Of course, I need to do the same. I need to have an empty array. Okay. And the axis is not defined, of course. Since I want to plot this in a subplot array type of array, so I need to do this. There we go. Ooh. So we have my different IPRs for each one of the pressures. We have a single VLP, and in that part we should be showing the intersection point. So let me check what's going on. Check. VLP rate. Subplots. I see. I didn't plot it. Yeah. There we go. So the reason of the error, I have defined the 2 plots beforehand, and what I did is just plotting this part, which is the first plot only. So I just needed to also add the second plot. And in the second plot, and we also have the labels. So I have the labels for the first plot, which is a sensitivity on reservoir pressures. And then we have what would be the solution. So reservoir pressure versus solution rate. So it's giving me each one of the solution points. And the conclusion is very straightforward. We know the higher the reservoir pressure is, the higher the initial rate, or the rate is going to be. Nothing else, it's consistent, okay? Pretty neat. So we can do the same now, but instead of changing the IPRs, I want to be changing the VLPs, for example. So I want to be changing the diameter, okay, of my tubing. And let's go. You are the same, reservoir pressure the same. The other parameters are going to be the same. So let's define now the two plots or subplots. And we have now a vector of rates going from 0.1 to this value, which is, I know, is above the maximum rates. And we do exactly the same. So, but now, let me rewrite this loop. In the previous one, we iterated, we went through for each one of the pressures. Now we're going to be going into each one of the diameters. And we have the IPR is going to be constant. We could also take this out because it's not going to be, in fact, we should do it because we have multiple evaluations without need of that. But for the VLP, it's going to be a calculation for every single diameter, okay? The procedure is pretty much the same to the previous one. And then there we go. Voila. Voila, no. Okay, I need to redefine. So this one is okay, the other one is not. And let me see why. Okay, I need to reset the solutions right here. There we go. So I'm just resetting here the previous solutions. And what we have here, a very nice graph intersection. So we have only a single one IPR, as we know. And we have 4 different VLP curves for each one of the diameters, okay? And then on the right side, we presented a sensitivity. The real result that we're looking for is, how the diameter is impacting the rate. And as we know, we should find an optimal point, okay? Which is, in this case, for these particular conditions, is telling me the bigger the diameter, the better in terms of rates. But we know this is a condition that is changing through time. So if my GOR is changing, if my any condition reservoir is being depleted, the tubing itself is being deteriorated, these results may change. But we know that, at least we can see here from this procedure that everything is consistent, okay? So far, so good. Any questions to this point? Okay, let me go ahead. I have something else to show you in rolling 10, 15 minutes, which is very short discussions on the functions, okay? The functions that we created in the PSA library so far are functions using scalar values. So a single value, we have the single set of inputs, we have a single set of outputs. And we're dealing with that and it's working fine, and that is fine, okay? But it might be in some cases where, if you're going to do iterations or going through a loop, if you want to run sensitivities, might be tedious, especially if we have something more elaborated, okay? However, as I mentioned, in the other part, the price, if we're going to do multiple sensitivities, imagine a case like this, when we have multiple IPRs and multiple VLPs. Writing this requires a little bit more of tricks because we are in a permutation case. So we need to make sure that for every single value is being evaluated with the rest of parameters. And it's going to be difficult to write in this case in this way. So we need to find some permutation cases. Adolfo, I need to check with you some possible solutions that we have. But what I wanted to show you is an easier way, or not an easier, probably a smarter way you can write an equation, but instead of using mathematical expression for every single value or every single operation that you need to do, you can use mathematical operations associated with a NumPy array. So let's make this more clear, okay? Let's do a function, very simple function. This is going to calculate the rate using the Darcy equation, okay? And I think we have it, it's written in many places. So we have rates in this function to calculate liquid rate using Darcy's equation, nothing else. And the function is like this. Let's say Q equals to, let's say, K times H divided by viscosity. Viscosity times the delta P, which is P minus PWF. Okay. Everything divided by parentheses 1.2 times oil formation volume factor times, I'm not so sure it's viscosity is right here. No, viscosity is already there. Times now, instead of using in a normal equation, we should be using math.log of RE divided RW 3/4, which is this, plus the skin. Skin is lowercase. Okay. In a normal, you should be doing this, but if we're using the array, we just need to change this by NumPy. So we're using NumPy array logarithm on this. So this is the only mathematical operation we have here. So if we have more mathematical operation, so we should be just preceding the operation by the MP. And then I'm going to return Q. So let's see what the difference is now. Now, instead of having one value of permeability, let's assume that I have a distribution, okay? So I have my permeability, which is a NumPy. I have a random variable with a normal distribution. And the mean of this value is 50. The standard deviation is 10. And I have a sampling of 1,000 values, right? And I can do the same for thickness. So I have, I know my thickness, the mean value is 25, but my standard deviation is in 5 units. And the same sample size. And the pressure, I also have uncertainty of pressure, and everything is going to be evaluated at a fixed flowing pressure. Okay. So what I can do, let's check. If I use seaborne, there is one plot, which is a disk plot, and we can go there. permeability. Next. So we can see that permeability distribution on this plot, and also a kernel function. Kernel function that is defining me this continuous line, and it's showing what we just input. My mean value is around 50, so the spread of this curve is plus or minus 10. We can see it very clearly, and we have a total of 1,000 values on this histogram. We can do the same for, if you want to make it bigger, probably just put the figure size, I don't know. You can define your size and make it bigger. So you can plot any variable that you want. But now let's use this function, Darcy rate. And I'm going to be passing to this function all these arrays. So we have, sorry, right here. We have Darcy rate, and passing the permeability, thickness, viscosity. See, yeah. So we have a solution. So if I write here Q, this is my array of solutions, okay? And let's plot this in a nicer way, okay? Sorry about that. Let's plot this in a much nicer way. So we have rates. Nice, no? So now I know that's the possible distribution of my solutions on rates. So it's telling me that the average or the mean value, is around 3,000, okay? Using this distribution, of course, we can change the type of the distribution. Instead of normal, we log normal or whatever type of distribution. And this is the beauty of using NumPy array instead of single mathematical operations. We can also take advantage of NumPy, for example. I can estimate what the P10 is, which is the percentile 90. So if I print P10, oops, sorry, it's not 110, it's P10. It's 4122, so which is around this value right here. Makes sense. We can do the same for P90 and P50, which is right here. Let's see if it's working. Perfect. And now I can also extract from NumPy the values of the histogram. Okay, assuming a bin size of 150, we can change this. It's not going to change that much, only the resolution. Okay, and what I'm using this because my target now, I want to build the cumulative density functions, and I need the values of this. So I can use the cumulative, which is nothing else than the cumulative of the values. Perfect, this is working fine. So if we go into cumulative, we print it, perfect, okay. And then we can plot it, okay? So we can have the maximum value. I want to normalize this from 0 to 1, okay? And I want to make this plot, okay? I'm plotting on the base That's what I'm getting all the base values. And I mean the rates, in other words, all the rates. And in the other side, I'm plotting the normalized cumulative distribution function, which is going to be from 0 to 1. And in this case, I plotted inversely, I mean, just to make, I mean, the lower value of rates going to the right. So it's something like this. So we have on the y the probability, and here the rates. And we can make more Dolce Gabbana on this. Let me put it more nicer for you. Okay, let's increase the size of the plot. Now let's make this that big. Okay. And what else I can do? Let's do an annotation. I want to plot, to include in this plot an annotation with the P90, P50, and the P10. And it's going to be like this. I can add a title if I want. Okay. We can add an annotation using this function, which is annotate. This is going to be a string, or this is the annotation itself. Okay. I'm just concatenating a label with the solution of my P90, and it's going to be located, my XY, on the P90 value that is already calculated on the X side. And the beauty of being normalized that I know it has to be on the 0.9. So we do the same for P50. And we do the same for the P10. Voila. Yeah. So we have now a distribution of what we are plotting here is rates, okay, versus the probability of having these rates, assuming this sampling right here. We have a sampling of rates, permeability, thickness, and pressures. Okay. So the likelihood, I mean, the median value is around 3000, 2986, which is pretty close, I mean, to the distribution side. Well, this is pretty much what I have for you in this morning. I hope you enjoy the session. So we still have some time for some question if you want. Some feedback. Your feedback is also greatly appreciated, so to make improvement for the future sessions. What we want to do on the next one is just to start doing more smart applications. Just instead of using a single well, we're going to be using real data from some fields and trying to do applications or calculations on batch. So instead of doing this for a single well, we can do it for multiple wells. We can do also regressions to estimate what the best operating condition would be. But any question, I will be more than happy just to share with you.
Well, this session has been sponsored by Dolce Gabbana.
That was a joke.
That was a joke.
I didn't have the chance to go through the chat. I'm just checking the chat right now.
Yeah, there is a good question from Jiku.
Jiku?
So he has 3 questions.
Yeah, let's say this IPR equation seems to be for black oil. That's correct. Will work for gas reservoirs, CNA for gas. Okay. This is only, as you say, a black oil. In order to work for gas reservoir, we need to incorporate these 2 or 3 models. We have Forchheimer, that's correct, and CNN, that's another model that is going to be easy to incorporate. And the beauty of one of that, you don't need to use the pseudo pressure calculations in some of them. Does anyone have experience in Python coding in IPiano per servers? There is one guy, I saw this guy on LinkedIn. He just translated the open server statements into Python, and my information is that also Petroleum Expert is moving from Excel into
VBA, yes.
Yeah. But what OpenServer does is basically you have OpenServer already have some functions predefined that you just call on demand and do the calculations using their software. So it's, if you will, is similar to what we're doing, but is instead of using my library or the PSP, the library the library is going to be Petroleum Expert. So, and they have, of course, a long run on this, and for sure it's going to be bulletproof.
I found a message from Sam Cottarelli, sorry. He's actually based in London, works in Toronto, and he's part of the community.
Mm-hmm.
He wrote an article in LinkedIn about this. I'm going to put the article here on the chat.
Yeah. Yeah. But OpenServer, I mean, we've been working with Petroleum Expert for a while. I mean, I know that they're really good on the work they do. It's, I mean, of course you have to pay for that. And any other question, feedback, or comments on this?
There was a third question from Jiku about.
Can you elaborate a bit on what you mean by neural nets on top of the? Oh yeah, well, it's just an idea I'm throwing. So for the time being, what we have is a very single solution of one point within the system. No? So we know the system is comprised by more than one element, and this is one of the elements. So depending on the configurations, we can do neural networks or artificial intelligence or whatever, based upon one objective function. Okay, so it can be from a single web perspective, especially they're doing a lot on well failures. So if you have enough information to supply for the well failures, I mean, you can do that. Or if we are doing it on a field basis and you have one variable that you need to optimize, for example, gas leak or energy consumption, or I don't know, a choke size, whatever, is similar to what GAP is doing. So you can, if you write the functions in the proper format, you can use the libraries already in Python to optimize or minimize, either by minimizing or minimizing an objective function. So this is what I meant on this. Sometimes you can also use this is purely physics-based solutions. But if you have something, only the data, you can use data-driven solution for this as well. Whether it work or not is up to your interpretation. That's the risk. Good. Okay, any other questions? All right, so if you can also write me and send me an email if you want you want to address any particular issue. I hope to be clear in this today's sessions, and I hope you find this very productive and useful, and you can find any applications on your.
Oh, yes, Jiku, this will be available in GitHub. Is it already available in the GitHub, in the EEG folder? I don't think so, no?
I don't think so, because I wanted to check with you. I messed it up last time and I don't want to do it again.
Okay.
So,
Okay, let's do it really later on today or tomorrow when we have time.
perfect. So you will have on GitHub this exercise as well as the previous one. And remember to install the psapy. And also we want to extend the invitation if you want to contribute or collaborate or expand on this. I mean, you are very, very welcome to do so, okay? And of course, if you catch any issue or error, let us know. Okay, it's been a pleasure to be with you this morning. So enjoy the rest of your day. And unfortunately, the weekend is almost over for most of us, but it's always good to have a weekend.
Yeah.
See you next time, okay?
All right.
Bye.
Okay, bye. Thank you, everybody. See you next time.
Bye, everyone.
Bye.